Okay, hopefully this is the last one. So we're going to talk about acids and bases now. Acids and bases are awesome things. I think they're very interesting. If you take 111, you will get plenty of information about acids and bases. We will not talk about it in a ton of detail. Right now, it's an introduction. We're going to define acids in very simplistic terms. We're going to then come back at the end of the semester and talk about like acid-base scales and pH and some of the interesting things that go with the math that goes with this. For now, we're just going to talk about some very basic reactions that go with this so that we can talk about titrations in a little bit. We're going to be doing some titrations in the lab in the coming week. So we'll be talking about that. And titrations are, in my opinion, very interesting, very tedious, but very interesting. They're a great way to learn things about the solutions that we're looking. And of course, if we want to talk about acids and bases, we need some definitions to be able to do so. For right now, we're going to define acids as solutions that give up H plus. And our bases as solutions that give up OH minus. So we've defined some solutions as giving up hydroxides or that can be named as hydroxide, sodium hydroxide, lithium hydroxide, things like that. And some solutions that give up H plus, hydrochloric acid, hydrobromic acid, hydriodic acid, those kinds of things. So HCl, HBr, HI. We tend not to include HF because it doesn't dissociate very well. So that's why that's not typically included there. Acids have sour taste. You know this. Lemons are acidic. They change colors of plant dyes. They react with some metals to make hydrogen gas. They react with carbonates and bicarbonates to make carbon dioxide. And they tend to conduct electricity. So that is something that they are capable of doing. Our bases tend to feel bitter, and that's because the soaps that we typically have known in the past have been made from lye, which is sodium hydroxide. So they tend to feel slippery, like soap. They do have bitter taste if you happen to eat one. They don't taste so great. They do change colors of plant dyes too, so not very helpful in identifying them. Aqueous-based solutions tend to conduct electricity, so again, not very helpful for identifying them, but they are also good conductors, and that's because both acids and bases can ionize, so they are capable of conducting electricity. So they're good electrolytes and therefore can conduct electricity. Okay. Now, Bronsted acids. When we talk about that definition that I just talked about as things that give up H plus or they give up OH minus, that was an Arrhenius definition. So there was this guy, his name was Arrhenius, and that was how he defined them. Okay. There's a more general definition that this guy Bronsted came through, and he said, well, that doesn't really suffice because it doesn't explain everything. We also have another base that we talk about, and that's ammonia. And H3 is a base that we typically do run into when we're out about and doing things. But it doesn't explain how ammonia works. Even though it acts as a base, it doesn't explain how it works. Because ammonia doesn't have an OH on it. So it can't be defined as something that produces OH. But it does exactly that. And that's because it reacts with water. So NH3 can react with H2O. And when it does so, what it does is the NH3 picks up one of the H's from the H2O and it becomes NH4 plus. And we're left with an OH minus. And so it does actually produce an OH, but not by giving it up. So there's that same OH production, but not in the same way. Okay. So that's why we have to change our definition just a tiny bit. So this OH is important. And we'll talk about why it's important when we get to the next definition when we talk about this at the end of the term. Okay. but it's a little bit different. And so our Bronsted definition has to do with this generation of OH minus in solution rather than direct donation of OH to the solution. All right. So now instead of talking about, it being an OH minus donor, we're talking about acids being H plus donors, and bases being H plus acceptors. Okay, so it's a slightly different definition. Okay, so Bronsted acids donate protons, Bronsted bases accept them. Okay? So slightly different definition. You will need to know this at the end of the semester. Right now it's not that relevant, but it's important that I explain it to you. Okay? And when we talk about acids, a couple of terms come up, one of which is protic acids. Now, what we mean by protic acids is that they have protons. And remember, when we talked about nucleotides, and we talked about nuclear chemistry, we talked about protons. Remember, we had that 1,1p. We said that it was, a helium nucleus or a hydrogen nucleus, and we talked about protons. Well, when we talk about protons, we're actually talking about that H plus, this H that we can deal with. And we said it was hydrogen nucleus. And so protons come from hydrogens, and they're typically what we're dealing with. When we talk about something being monoprotic, it means it has one proton. If it's diprotic, it has two protons. If it's triprotic, it has three. So we can talk about our monoprotic acids, HCl, HBr, and HNO3, CH3, COOH, all have one proton and they can donate. Notice that CH3 has a bunch of H's on it, but only one of them they can donate. Okay. Diprotic, H2SO4, has two protons that it can donate. It does so in two steps. So H plus HSO4 minus. HSO4 minus can also donate one H plus to leave SO4 2 minus. There's one common triprotic acid that we talk about. It's H3PO4. And again, it acts in steps. So H plus H2PO4 minus, H2PO4 minus plus H plus HPO4 2 minus, and then HPO4 2 minus goes to H plus PO4 H or PO4 3 minus. Okay, so multiple steps. So one proton, monoprotic, two protons, diprotic, three protons, triprotic. Any number of protons is protic. Okay. All right. Our Bronsted bases accept a proton. They do not necessarily all produce OH minus, okay, but they can accept a proton. Right? The accepting of the proton from solution is why they are defined as a base. Since NaOH completely reacts, it is not a reversible reaction, so it doesn't have that double-headed arrow. Okay, but NH3 is a double-headed arrow because that reaction can go in both directions. All right, so that's what we're talking about when we talk about a reversible reaction. We've mentioned this before. All right, so that is a weak base. NaOH is a strong base. Okay. Now, we also have a process that we talk about, which is called acid-base neutralization. It's a common term for us to use. When we talk about your stomach being upset and we say that we need to neutralize the acid in the stomach, this is a common term. We're talking about taking an antacid because your stomach has acid in it. And so we give you an antacid to try and neutralize the acid in the stomach. Okay? We're trying to get rid of the acid in the stomach by giving you a base to neutralize it. And what we're trying to do is get the exact right amount of base added to your stomach so that there is no acid left. It's a really difficult process to do. Often goes wrong and we go too far the other direction and you end up feeling bad in the opposite way. But this is a process that we try and do. It's something we try and do in the laboratory. It's something that can be very difficult to do. It's hard to get right. We have to monitor it a lot. It has a lot to do with not only how much of what we add, but also what concentration those things are. So we need to know not only what the volume is, but also the concentration of what we're at. We'll talk about concentrations in the next lecture. We're going to be talking about the concentrations of solutions in the next lecture, and that'll be defined as moles of material per liter. And so we'll talk about what that means when we talk about that. But that is another important component of what we're talking about when we talk about that. But neutralization means that we've added the exact same amount of acid as base. Okay, so that would be a complete neutralization reaction. And at that time, since we have the exact same amount of acid and base, then everything has become water. All right. If we don't get it right, then we have either too much acid or too much base, and that's a problem. Okay. So if it's equal, then we've neutralized it. If not, then we have too much of something. Okay. And we have to deal with it. So we want to talk about neutralization and those reactions that we see. So we want to write the molecular, ionic, and net ionic equations for the following reactions. Now, I'm going to pick two of these, and I'm going to do these in detail, and then I'm going to have you do the other three, and we'll come back and give you answers for those. So, like I've done before, I'm going to choose two, I'll do those, and then I'll give you answers for the others. So I'm going to pause here, and I'll be back in a couple of minutes. Okay, so as always, I have changed my mind, and I'm actually going to do three of these with you, and I've given the answer for the other two. So we're going to trade partners just like we always do. And so I have K with BR, KBr, K plus, BR minus, so KBr, and H plus and OH minus, that's H2O. Now I did this one right here, and I have H, 2H plus, 2 OH minus to give the H2O, and I end up having two of them. And then I have SO4 2 minus, and that means I need 2 Na plus to make Na2SO4. Okay, so those are the two that I just gave you answers for. Now, I'm going to go ahead and do this one, and I'm going to walk through this in detail. So I know that this is Ba2 plus and 2OH minus. I know this is H plus and I minus, right? I know those are the ions that make those things up. So if I'm going to trade partners, I'm going to have OH minus go with H plus. And that means I'm going to get an H2O out of that. Since I have two of these OHs, I need to have two of those H's. And that means I need to have two of the I's also. So two of each. So I put a 2 out there. And so I end up with two H2Os. Right? And then this is a Ba2 plus, and since it's a Ba2 plus, I need to have two of the I minuses. And oh look, there's already two there because I put the 2 out in front of it. So it's a BaI2. Okay, so the balancing works because I had to do that. Now, typically what we find is that if there are two OHs, I'm going to need two H's to go with it. So that's just a little hint for you with how we're going to need to do that. I'm going to skip this one for a minute. I'll come back to it. But I want to do this one. And what I see from this is that I've got an H plus, an NO3 minus, K plus, and an OH minus. So I know I'm going to make an H2O, and I know I'm going to make a KNO3. Now, it may seem like I'm going through this really fast, and I am. One of the things that I have learned as I've done this is that we have certain types of reactions. I talked about combustion reactions, and I said that was always something reacting with oxygen to give carbon dioxide and H2O. That's true. These are neutralization reactions, and so we're always reacting an acid and a base to give us salt and water. Acid, base, salt, water. And that salt is just an ionic compound. So I'm always taking the thing that's here and the thing that's here and making water. So it's very easy for my brain to pick out what that's going to be because I've done this so many times. Repetition is really useful for this. And I've learned to see patterns. If I see two OHs here, I need two H's there, and I make two waters. If I see three H's here, I need three OHs here. I make three H2Os, and then I'm going to need C3K3PO4. I mean, it's just one of those, because I know that there are three of these because it's a PO4 3 minus, and that means I need K3 PO4. It's just pattern recognition, and it's based on the charges that we see. That's why it looks the way it looks. So it becomes very quick for me to do this. And that's why for me, this becomes very easy. But that's because I've done this 1,000,006 times. So practice will help you for doing this. It makes it a lot easier if you've done this 1,000,000 times. Okay? If you know the patterns, it makes it a lot easier to understand what you need to do. Okay? So that's what we have for that. Questions, comments, problems on what we're doing there. Okay. I have given you lots of practice, so hopefully you can become as proficient at this as I have. Okay. Well, so far, it's looked like this is the easiest thing in the universe, right? We take an acid, we add it to a base, it's always this lovely equation, boom, we're done. Is it always really that easy? Well, not always. Because I know that some acids are strong and some bases are strong and some acids are weak and some bases are weak. So what happens if I'm reacting them together? What happens if one's a strong acid and one's a strong base? Well, strong acids react with strong bases, and in theory that reaction should go to completion and that should be fine. But what if that's not the case? So it says weak acid, strong base here, right? So HCN is a weak acid. It's not a great acid. And NaOH is a strong base. So when we do this reaction, we get H2O that's made, and then NaCN, right? And NaCN, there's nothing, it's not insoluble. So we end up with Na and CN in solution in H2O, right? But that is an interesting thing that we have. So that Na and the CN being in solution, that Na doesn't want to react with anything because it's perfectly happy. It's not going to react with parts of water to go backwards and give us that NaOH back because it doesn't want to. But that CN, it's not overly happy being the way it is. It wants to react with water again. And it'll walk up to a water and say, you know what, water? I want that H back. And it'll yank one off of water and say, give me that back. I want it. And so you'll be left with an OH minus, and you'll get that HCN back. Because it wasn't a great acid to begin with. So it'll give you that acid back, and you'll be left with this OH that's in solution. And that's going to change stuff. Because I end up with that OH that's left in solution, that's going to change the pH. Now, we haven't talked about the pH yet, but that's going to change our pH, and that becomes a problem. Okay, so that's something that we have to be aware of. When we start talking about changes in pH, that's going to become an issue. So because this CN minus is the conjugate of a weak acid, it's something that we have to be aware of. It's being in solution. Okay. There is something in your exam handouts that talks about what happens when we have stuff in solution. It says properties of salts. If we have the cation from a strong base and the anion from a strong acid, then there's no effect. That's what it says. And so it's approximately 7. But if the cation from a strong base and the anion from a weak acid, which is what we were just talking about, then we have to worry about that anion. That's Cn minus. And the pH of that solution ends up being above 7, which is exactly what we're talking about right here. Okay, so that's something that eventually we're going to end up having to talk about. Okay, that is a prediction we're going to have to that we're going to expect you to be able to make. And this is why. It's because that anion will react with the water to give you back that weak acid. Okay, but that will be here for you to be able to reference. Okay, so that is a thing. It's something that's going to happen, and we'll be able to talk about it in more detail when we talk about pH. Okay. Now, other things. Acids and bases can react to form gases. So if we have a reaction that makes like Na2CO3, and we react that with an acid, we'll end up making 2NaCl and H2CO3. Now, this H2CO3 not particularly stable, and it spontaneously decomposes to become water and CO2 gas. That CO2 gas or an SO2 gas can can just pink and go off by itself, and suddenly things do not look the way that they looked 2 seconds ago. All right, this can be useful, or it can be not useful at all. All right, we can use this in the laboratory to determine how much of the starting material we had. We can drive that off and then measure the salt that's left, so the NaCl that's left, to get some stoichiometric measurements of how much of the stuff we started with. We can drive this reaction to completion to get rid of the CO2 and then figure out how much of this we had. There are a number of things that we can do to make this work for us. All right. But we have to be aware that some of these things can form gases, and therefore we have to be able to deal with the fact that can happen. So it's something that can happen spontaneously in the laboratory, and we have to be able to deal with it. Okay? Questions, comments, problems on that? So what are things that I talked about today that actually matter to you? So acids can donate H plus to solution. Bases can either accept OH plus or accept H plus or donate OH minus, either one. Strong acids and strong bases are listed in the table on the exam handout. If it's not a strong acid, it's weak. I don't care if it's in the exam handout or not. If it's not a strong acid, it's weak. If it's weak, it can react with water to form the protonated acid again, thus producing OH minus and raising the pH. Weak bases can donate their proton to water as well, thus lowering the pH. Some clear solutions, when mixed, can produce a solid that's said to be insoluble. Insoluble products are something we can predict using the solubility rules. Okay, so you need to be able to predict insoluble products. You need to be able to predict your products by changing their partners. You need to be able to write and balance equations based on the information that you've been given. You need to be able to write molecular, ionic, and net ionic equations. Okay, and you need to understand why you might have reason to do any of those things. You need to remember that your net ionic equations need to be able to show anything that has changed phase, has either become a solid or a liquid. Okay. You need to make sure that you can include the phases for things. So when we're talking about solubility, everything should start out as an aqueous component. Anything that is soluble will be aqueous. Anything that is not soluble will be a solid. And you need to be able to predict those. You need to be able to tell me based on what kind of thing it is, whether it's a strong electrolyte or a weak electrolyte, and then tell me whether it's a good conductor, not a conductor, or a good conductor, weak conductor, non-conductor, based on its electrolyte properties. Okay. And you should be able to predict whether something is an acid or a base or a neutral. Okay. So if it can donate H, it's an acid. If it can donate an OH or take, accept a proton, then it should be a base. And if it can't do either of those things, then it should be neutral. Okay, so those are the expectations for that. All of that is for the second test. Should not be a problem for you, and we will talk about it lots, and there's lots of practice for you. So questions, comments, problems on our Aqueous solutions. All right, so we will talk about concentrations next time. After our concentrations, we will completely flip the script and be talking about molecular geometries and how we can predict those. So I will talk to you again soon, guys. Thanks.